All right. Yes, sir. Yes. Okay. So what we're going to do, guys, we're going to continue to talk about and work a few more problems. We did a cart. We did the cart and the ball thing, right? Yesterday. Is that correct? Yes. Yes. Okay. Did I do? I can't remember. Did I do the problem where the guy jumps off? Did I do that yet?
In the ball falls off the cart.
Cart and the ball.
Well, we also had the one where he was going down the slope.
Oh, that was like last week. That was last week.
We never finished that one. No, that was like 2 days ago. Yeah, we never finished it.
Okay, that was let's and do you have it written down?
Yeah.
Okay, can you tell me what it is? It might be similar to what the ball was, but let's see what you want me to do that one, or let me see. Just tell me what it was.
So he was going down the slope like that.
Yeah.
And then the height was 300 meters, and then there was another height of 100 meters. And there's VX and VY.
Okay, and he's sitting here. He's skiing, right?
Yeah.
Right.
VX and VY.
Okay, and there's Vx and Vy. So what's the Vy?
It was a 0.
0, right? Equals 0.
He had to release his chute at 100 meters.
How much?
100 meters, he had to release his chute.
Okay. All right, and then
And it didn't have VX.
did it have a Vx?
And there wasn't no.
Yeah, you said we were going to.
All right, I'm going to modify this. I'm going to modify it slightly. I'm going to give him a Vx. All right. So I'm going to give him a Vx. We'll modify this problem slightly because this will actually be similar to the problem I was going to do anyway. So Vx. Let's say he's got Vx at 30 meters per second. That's his velocity. Okay. So he has purely horizontal velocity and no vertical velocity. Okay. So he is going to travel out here, and the question ends up being, have I done a problem like this where I ask how far he goes?
Well, you said that he had to like release his chute at 100 meters.
And like,
Yeah, hold it.
how long,
And what was I asking about
like how long.
the time?
How much
Okay.
time does he have?
All right. Well, let's do this. Let's do that. Let's say that let's do that. So he's going to be doing one of these things, right? Okay. And at 100 meters, oops. That's where he's got to put that chute. Ideally. Right? So the question is, how long is it going to take to do that? What time, what's the time for this to happen? All right, so let's think about this for a second. What's happening? What kind of motion does he have? Constant acceleration, which direction? Down. What else does he have? What other motion does he have? He has horizontal motion, right? And what kind of motion is this? Horizontally. Well, let's think about that. In order for him to, if it's not constant, what does that mean? It means that the velocity. Yeah, his velocity is either increasing or decreasing. Assuming no air resistance, his horizontal motion, is there anything stopping his horizontal motion? Anything increasing his horizontal motion? Nothing. There's no other force. Once he leaves that, the force is pulling him down, but horizontally, that velocity isn't changing because there's no rocket engine on his back. There's no air resistance. Nothing is going to change his velocity, okay? So at this point, his horizontal velocity is constant because there's no additional force that's actually making that happen, okay? So he's got the two different motions, and the vertical motion is what kind of motion? What kind of motion does he have vertically?
Gravitation. Negative.
Okay, say it again, Courtney.
Constant acceleration.
Okay, the kind of motion that he has going vertically is what, guys? Everyone say it. Do we understand why that's the case? Okay. So we have constant acceleration, and that's due to what? What? To gravity, right? And what's that constant acceleration rate due to gravity? Negative 10 what? Meters per second squared. Okay, that's his rate. All right. What kind of equations do we have to deal with constant acceleration? There are two. What are the two equations that we have? Delta D equals what?
Equals 1/2 a times delta t squared.
Okay, what's our other acceleration?
It's velocity
Yeah, acceleration is change in velocity over change in time, right? Okay. So we have our two basic equations. Now really listen up. There's an extra term out here. What's the extra term out here? Someone remind me what the extra
initial velocity
times delta t. Don't forget this. Oops, I'm getting too close to the edge of the screen. Don't forget this term. That term is the amount of distance that he travels if he had an initial velocity. Okay? So vertically, what's his initial velocity?
0.
0. Does everyone see that? When he leaves that slope, he's leaving purely horizontally. That means the instant he leaves that slope, he has 0 velocity. Okay? Downward. So that term here, in this case, this term does what? What happens to this term here? If his initial velocity is 0, what happens to this term? If V naught is equal to 0, what happens to this term? Jude? Goes away, right? Okay. Okay. So now we're looking for time. Let's think about what we have. We're looking for time, right? We have the height he starts at, the height at which he needs to pull his chute, right? And we have his horizontal velocity, okay? Let's think about this. So which direction of motion do we think is going to get us to this timepiece? Courtney, you think the vertical motion, okay? What about let's for a second, let's try the horizontal motion, right? This is all for the constant acceleration for the vertical. The horizontal, what's the horizontal motion? What kind of motion is it horizontally? Everybody? Constant velocity. So constant velocity is equal to what? Delta distance over delta time, okay? So if we knew, given this, listen, here's the best part. The equations that govern the horizontal motion are always going to be true, even while the equations for the vertical motion are always true as well. So I could try and solve this with either of the two motions. The question is, for which motion do I have all the information for? This is important. This is your strategy. Okay? Let's look at the horizontal velocity, the constant velocity horizontally. That means I have three variables: velocity, change in distance, and change in time. I have to have those. I have to have at least two of those to solve for the other. Correct? I know that what component connects both of these equations, both of these sets of equations? What's the one thing that connects them both? Time. So we know that the time, if I'm looking to be at the same place at the same, it's going to be always the time, right? So if I'm looking for the time here, either way I do it, it's going to be the same. It's going to be the same time. So given that case, I'm looking for this time. In order to do that, I'd have to have either since I don't know time, I have to have the other two things. I've got to have velocity and distance, right? Do I have the horizontal velocity? Yes. Do I have the horizontal distance?
You have the distance.
But do I have the horizontal distance? Because remember, this is all about horizontal motion. Do I have okay, so I'm stuck. I cannot use the horizontal motion to solve this problem because I don't have enough information. Do you guys see that? Very important. Any questions on how I got there? And you're going to try it one way, and you're going to say, oh, that didn't work. Let me try it the other way. Okay? So we know that this isn't going to work initially because I don't have the distance. But let's look over here. Okay? I can look at this scenario here. I have my acceleration rate. Do I know what my acceleration rate is?
Yes.
For vertically. Vertical motion, yes. It's that due to gravity, which is negative 10 meters a second squared. I'm looking for my delta time. Isn't that wonderful, right? Do I have my change in velocity? Well, let's think about that. What does delta velocity equal? V final minus V initial. Well, do I have my initial velocity? Yes. Do I have my final velocity? No. So again, I've got a scenario where I've got two unknowns, time and my final velocity, which means I don't have my delta velocity. Do you guys see that? So I can't use this equation either. So now, let's go over to here, okay? Let's look. Again, time is in here. My initial velocity is 0, so this term goes away, right? Which is nice. But I'm looking for my time. Do I have my acceleration rate? Do I have the change in vertical distance? Okay. But do you see, when you say vertical question, I want to make sure, Daniel, that you know that, look, this is about the vertical portion. Now, by the way, could I use this for horizontal motion? Sure. But that would require my horizontal motion to have constant acceleration. And that's the next problem we're going to do. Okay? But for the vertical case, you notice now, again, it is all about drawing the picture, laying out your facts, and once you have your facts, what you have and what you don't have, then that's going to tell you which equation you can use. Sometimes, by the way, in certain cases, you can use multiple equations. You might be able to do it two different ways, and you can do that. But only until you lay out your facts, you know what you know. Okay? One of the methods I like to use, and I don't want to require you to use it, but I would highly suggest you do it, is this. I would lay everything out. I would say, okay, for my horizontal, I'm going to have all the different possible variables, right? I've got d final, d initial, delta t, because we're going to assume that we're starting at 0, okay? And our velocity, okay? And you can make a little chart. And you say, okay, do I have distance final? I don't. Do I have distance initial? I don't, horizontally. Do I have my delta time? That's what I'm looking for. Do I have my velocity? Yes. I can all of a sudden see from this table, I don't have enough information right away. You see that? I can do another table. Let's look at this. Let's look at, in this one, for the vertical, okay, I can have a whole bunch of things. Velocity initial, velocity final, right? And I've got my acceleration rate. I have my distance initial, my distance final, and my delta t, right? So I've got all of that stuff. These are all my possible combinations or variables I can have. Do I have my initial velocity vertically? Vertically, do I have my initial velocity? Yes. Do I have my final velocity? No. Do I have my acceleration? Yes. Do I have my initial position? Yes. Do I have my final position? By the way, what is my initial position? What is my final position? What is my delta position? Negative 200. Final minus initial. Guys, don't mess that up. That will mess you up. Don't do that. Okay, and then I'm looking for my delta time. Now I have everything sort of in a table, but I can then go look at my equation and say, okay. And if you do this, you will know right away which equation. There will not be, well, Mr. A, which equation do I use? It will tell you. You see how that works? Okay, you can solve the most complex problems doing it just this way. All right. Okay. So given that, all right, we know that having done that little bit of analysis, we know that we're going to use which equation to figure out our time? Which equation are we going to use?
We can use
Well, which equation are we going to use to find that? Because we're looking for delta time right now. I'm looking for the time to throw the parachute, aren't I?
So use the vertical.
Okay, we're going to use a vertical motion. And which equation are we going to use?
Delta D equals 1/2 A delta T squared.
Okay, so we're going to use the delta D equals 1/2 A delta T squared plus V naught delta T, right? This goes away because our V naught is 0, right? So our delta distance is what? It's D final minus D initial, okay? So D final is what? What's my final position? 100 meters. What's my initial position? 300 meters. Equals 1/2. What's my acceleration rate? And then and I'm looking for my delta time squared, right? So now I'm going to do negative 200. Okay, oops. And that's going to be negative 10 times 1/2 is negative 5, right? So divide by negative 5, right? So divide by 5 negative equals 40. So 40 equals delta time squared, right? And the square root of 40 is 6.32 seconds. So delta T is equal to 6.32 seconds of air time that he has to think about pulling a chute. Okay? Yes, ma'am.
Wait, what's the little V naught times delta T? I know you're not doing it, but what do you mean by that?
Okay. Remember, I'm going to hide this for a second. Remember when we talked about, remember we talked about, sorry, I'll come back to it. I didn't delete it. It's right there. I promise. Hold on. Remember we talked about the truck scenario. Remember we talked about, if I look at velocity versus time, right? And I'm going to accelerate. I'm going to do constant acceleration, but from an initial velocity of 0. So I'm at the stoplight, the light turns green, I hit the gas. My velocity versus time graph looks like this, right? Velocity is increasing as time goes on, correct? Yes, because I'm going, right? So if I want to know the distance that I've covered, right, it's the area under this curve. Do we remember and believe this? This is important, okay. If I'm going a constant velocity for a certain amount of time, right? 50 miles an hour for an hour, I'm going to cover 50 miles, right? So this delta D is delta D for constant velocity is V times delta T, right? Okay. This delta D for acceleration was 1/2 delta D equals 1/2 A delta T squared. Now really it's 1/2 V times T, or delta V times T, but delta V is really, I don't want to rederive that. Do you want me to rederive that? Do you want me to rederive how I got that? Okay. But this is for acceleration, okay? So here's a scenario. So these are independent of each other. This one doesn't have acceleration. This one has an initial velocity of 0. But what if my motion looked like this? Okay, velocity versus time. Okay, I'm at a constant velocity, some sort of initial velocity V naught for a certain amount of time. I'm going to cover this distance, aren't I? Right? Because it's constant velocity. But the moment I start here, I'm going to accelerate and cover all of this distance, right? But because I heard to accelerate from some velocity other than 0, I'm actually going to be covering more time. So the idea is that if I were to, so this is the idea that I'm traveling on a highway next to a big semi. We're all going 50 miles an hour, but I want to pass a semi. So we're going 50 miles an hour for the first time. Then I want to pass it, so I have to accelerate. Okay? It's an alternate reality thing. It's a choose your own adventure, right? If you didn't pass the truck, then you would have covered this distance anyway. You follow what I'm saying? But because you accelerated from that, you're going to also cover more distance on top of what you already would have. So this portion here is my v naught, my initial velocity, times my delta time. That velocity I was originally going before I accelerated. Make sense? Plus the delta distance of 1/2 a delta t squared. So my total change in distance is, due to my acceleration, 1/2 a delta t squared, plus any distance I would have carried, I would have passed or gone through because of my initial velocity. Does that make sense? Courtney, you good? Any other questions on that? Okay. That's why there's those two things. So there's our time. Everyone understand how we got this time piece? Now, what can I do with this time? Talk to me about what I can do with this time. What?
You can find the horizontal.
I can find the horizontal distance, right? How would you do that?
You take the horizontal velocity that you have and apply it, and then it'd be v times delta t.
Yeah, right. You totally could do that. What else could you possibly do? And this may be a stretch to ask you this, but what else could you possibly do with that information? A couple other things you could do. Come on, take a guess. What else could you possibly?
Find when he hits the ground.
You could potentially, eventually find when he hits the ground, right?
Is it linear? Because then you can predict from what height, like any height, you get the trajectory.
You can predict from any height, but it's not linear because the fall rate is quadratic, right? So it's not a linear thing at all. But you can predict. At this point here, what can you predict though? What could you also predict? What stuff didn't we have? Think about these equations. What did I not have?
The final velocity in the y.
Yeah, you can figure out the final velocity and the y. You can figure out how fast he's going when he pulls that chute. Right? Okay. So you can figure. How would you figure that out?
You have to have acceleration.
We've got the acceleration due to gravity.
Plug it into the delta t, and then delta t, and then so it's acceleration times delta t.
Okay, good. So do me a favor. Figure out the final velocity on your own here. Figure out the final velocity and the position horizontally that that he's at. So where did he go to here? So do that now. You guys independently and in a group, figure out those two things. What is that distance that he traveled horizontally? What's his position? And so that delta D or delta, I'm going to call it delta X. Okay, we'll call it delta X. What's that change in X? It's a delta X, right? And what is the final velocity in the Y? VYF. Okay? Do you guys see why I put VYF?
Yeah.
Okay. All right, go, 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 go. Go, go. If you're lost, you don't know how to start, talk to someone next to you. Someone's bound to know. We just talked about how to do it.
It's like a
Step off. The other part of that, Jude, is you need to step off.
For some big free agents, and probably overpay some of them, but it doesn't hurt them at all because all it is leftover money from last year.
That's not bad. I think it was a very smart move by the Cowboys to franchise him.
I was never for sure.
Yeah, because now they have a whole year, or not, well, not really. They've got the year to position out there, and then that buys and power just over some.
Yeah.
So break up double D. This is the initial.
There's not, you can't, you have to pay.
Yeah, you gotta keep.
Alright. Okay. Do you have an answer? Come on now, we just talked about how to do this. Then do it. It should take 8 minutes. Do it. Stop talking. You know how to do it, then do it. If you don't, you good? You good? Is the answer? Alright. You guys over here?
For which one? Last year. Or finalized last year. And X is horizontal.
Is the note of 3 seconds?
So what we're trying to say is, where he's, and it doesn't matter where he's going, where horizontally he is. Okay, so he's gonna, when he jumps off, he's gonna do. And at this height, he's gonna pull the chute, right? But I want to know how far away from the cliff horizontally is he when he pulls the chute. Okay? Maybe there's a tree. I want to make sure I clear this tree.
I just put it into
I want to know horizontal.
equals W.
And the idea is that we figured out in the first part the time, right? The time for him to get to the time for him to get to this point. He's going to get to this point. To get to this point, he's got to travel horizontally and vertically. And when he's at this point, there is some portion of horizontal motion that has occurred, and there's some portion of the vertical that has occurred, and they both occur at the same time. Right? That's the link between the horizontal and vertical. Okay? So in this case, since we figured out our time, did you follow how we figured the time out? Did you get that? Okay. What governs where he is horizontally? What's going to define where he goes horizontally? Not gravity. Horizontally, just his velocity horizontally.
Okay, so for
The
velocity to line,
horizontal motion is going to tell you where he is horizontally. You're completely
but now,
independent.
so I gotta
Vertical
reduce the
and the horizontal. The only thing that's
So you got that right.
the horizontal is stop the motion. So he's going at 30 meters a second horizontally at a constant velocity. Means his velocity is changing. Okay? So that's very simple. I'm going to get So at this point, I can use, if I have my velocity, which I do,
So,
I have the
see how
delta
that
time,
goes.
which we figured out at that point. I have to figure out the delta distance horizontally. Okay?
Yeah.
You see what I'm saying?
Mine's just super short. Like, I don't even think I have a third.
Alright. Okay, let's go over this, guys. Let's go over this quickly. Yeah.
I was just lazy last night.
I'm gonna do it right now.
I think you're right.
Okay. Shh. Okay. So let's think about it. So in order to figure out his horizontal position, guys, What governs his horizontal position? What's going to determine how far he goes horizontally? His horizontal velocity and the time it takes to get there, as long as he doesn't hit the ground first, right? So since I know my time, I can plug my delta t into my horizontal velocity, constant velocity equation. Do I know my constant velocity? Yeah, so v equals delta d over delta t, right? And my velocity is 30 meters per second, equaling my delta distance is what I'm looking for, right? Over my delta time, which is what? 6.32 seconds. That means my delta distance is going to be 30 times 6.32, right? 6.32 times 30 gives me 189.6 meters. 189.6 meters. Does that make sense? Okay. Now the question is, what's his velocity? What's a vertical component of his velocity? That's what I want to know. What's a vertical component of his velocity? How do I figure that out?
Delta V equals A times delta.
Okay, so our acceleration is equal to delta v over delta t, right? And where delta v is actually, so if I look at delta v equaling a times delta t, but delta v is really what? What can delta v be broken down to? V final minus v initial equals my a times delta t. What's my final velocity? That's what I'm looking for. What's my initial velocity? 0 meters a second. What's my acceleration rate? Meters per second squared times my delta t, which is what? Which is what? 6.32 seconds, right? And so then I can say, all right, 10 times, it's going to be negative 63.25. Why is it negative? It's going down, so his velocity final is equal to negative 63.25 meters per second, because it's it's meters per second squared times, it's meters per second squared times, yes. That's why you do the units, to double check.